To clarify it, let's give a few examples. Consider a mass of unit mass, m equal 1, which is put here in the position 0, 1, and 0. So let's see what is the rotation that the different forces will lead to. A force in x is going to produce a torque in the z direction, and a force in z is going to lead to a rotation around the x-axis. To see this, just use the right-hand rule to find where is the torque. Remember, the torque is the cross product between the arm, and the force. And a force in y does not have an arm, so it will not lead to rotation. So let's see how the inertial tensor describes this behavior. According to the tensor, if you put here x equal to 0, y equal to 1, and z equals 0, these are the terms that you get. You can then write to the inertial tensor. That's almost an identity matrix, except that the y component of the diagonal is 0. We can compute from that the relation between torques and acceleration, and then writing it in components, we have the three equations for the torque in x, y, and z. So what we see here is that the y direction cannot be torqued. That's what we got from the graphical representation, doing the right-hand rule. Now the torque in x, which is a force in the z direction, is only producing a rotation, an angular acceleration around the x-axis. As expected, you put a force here in the z direction, it produces a torque in the x direction. That's the only acceleration that you get, a rotation around the x-axis. Now, a torque in z, which is a force in the x direction, is producing a rotation around the z-axis only. You have a torque in the z direction that gives you a rotation around the z-axis. This is what is exemplified in this figure. You have a force in the x direction, produces a torque in the z direction, and is the only direction where you have an angular acceleration.